Hello, we're going to be considering the following model, where our dependent variable y is the log of production. Our first independent variable x is the log of labor, and our second independent variable z is the log of capital. So this model is a Cobb-Douglas production function that has been linearized using the natural log. For this problem, we are given the following results. We are given the XTX matrix. We're given its inverse, XTY, and the sum of YT minus Y bar squared, which is the total sum of squares. So for the first question, we are asked to determine T, X bar, Z bar, Y bar, and so on. So we'll be using Excel for convenience. The objective of this question is to make you memorize the general format of XTX and XTY. So the number of observations T is the first element of XTX, which is 23. X bar is the sum of XTs over the number of observations. So it is the second element in the first row of XTX. So it's 230 over 23, which is 10. Z bar is this element divided by T, which is 5. Now for Y bar, we're not going to be using XTX, we're going to be using XTY, which has this general format. So the sum of YTs is the very first element of XTY. And we just divide that by the number of observations. Okay, so next we are asked to calculate the sum of xt minus x bar squared, which is, as we discussed before, equal to the sum of xt squared minus t x bar squared. So the sum of xt squared can be found here in XTX. And the second part is T times x bar squared, which is 100, and subtract this from the first element, and we find 12. So the sum of xt minus x bar squared is equal to 12. We calculate the sum of zt minus z bar squared using the same way. Sum of zt squared is this element, and we do the product of t by z bar squared. So it's also 12. Now we're asked to do this term, which is the sum of xt minus x bar times times zt minus z bar, which is equal to the sum of xt zt minus t x bar z bar. So the sum of xt zt is this element, and the second part is t times x bar times z bar. And it's 8. So the sum of xt minus x bar zt minus z bar is 8. Next, we're asked to determine the sum of yt squared. So we're going to be using the same method to find it. The sum of yt squared is equal to the total sum of squares plus t y bar. We have been given the sum of the total sum of squares. So we just add t y bar squared. So it's equal to 10. Let me show you the total sum of squares. It's given here. So it's 10 plus t times y bar squared. So it's 3,322. Next, we are asked to calculate the sum of xt minus x bar times yt minus y bar. We use the exact same formula we used before. So sum of x times y. We find it in the xty vector. So it's the second element in that vector. The second element. And the second part is t x bar y bar. We're also asked to do the same thing with z. So we'll be using the last element in xty. And the second part is t23 times z bar times y bar. So it's 8. We have now finished the first question. Let's look at the second question. So we are supposed to determine the beta OLS, which are the estimates of the regression coefficients. So as we've already discussed before, the beta hat, the beta OLS, is found using this formula. It's xtx minus 1 by xty. So at the beginning of the exercise, we are given xtx minus 1 in this format, which is 1 over the determinant by the adjoint matrix. So to find xtx minus 1, we have to divide each element by 460. And here we have to be very careful with rounding up or down. If we do rounding up, we're going to be finding very different results for the beta OLS estimates. So we can do this manually by just dividing the elements given in xt in the adjoint matrix by 460, or we can use Excel to just find the inverse based on xtx. To do that, we could just select these cells, go to function, and write mean-verse. Then we select XTX. Then we hit Control, Shift, and Enter. Here, we easily found the inverse of XTX. Maybe you'll find this useful while working on projects. Okay, so we're going to be multiplying XTX minus 1 by XTY. To do that, so when we're calculating the product of two matrices, we do row by column. So the first beta 0 is equal to the first element by the first element in the second matrix plus minus 1 times second element plus 0.25 times. So it's 4. The second one, we do the same thing. Go to the second row. It's 0.7. So it's 0.2. So beta 0 is equal to 4. Beta 1 is equal, beta 1 hat is equal to 0.7, and beta 2 hat is equal to 0.2. We're asked to interpret, yes, we're asked to interpret economically beta 1 and beta 2. So this is a log-log model. So the coefficients beta 1 and beta 2 represent the elasticity of the production with respect to the labor and capital, respectively. But we have to mention when interpreting the very first coefficient, for example, we have to mention that we are holding the other regressor, capital, constant. This is called the ceteris paribus concept, which we have discussed before in class. Okay, let's actually write down the interpretation. So let's interpret beta 1. So beta 1 is a proxy of the elasticity of the dependent variable y, which is the production with respect to the first independent variable labor with respect to labor, given that the second independent variable, capital, given that capital is held constant. So we do the same thing for beta 2, except that we have to say that we hold a labor constant. Okay, so next question is determine the estimator of sigma squared. Sigma squared is the variance of the error terms, which is constant based on the assumption of homoscedasticity. Okay, so to do that, I'm gonna use Excel as well. So to find sigma squared, we have to divide the residual sum of squares by t minus k minus 1, while k being the number of independent variables we have. So we start by calculating the residual sum of squares using this formula. The first part is the sum of yt squared, which we can find here in the preliminary calculations we already did. Then we need beta hat transpose, which is this one transposed. So we just have to copy it and transpose it. Never mind, you can just write it down. It's only 4 elements. So 0.7, and this one is 0.2. So next we have to calculate beta hat transposed times xty for this entire part. So it's equal to, again, to do the product of two matrices, we do row by column. So it's equal to 4 times, let me find xty, plus 0.7 times second row so it's 3320.6. So the residual sum of squares is equal to yt squared, the sum of yt squared, minus the second part, which is beta hat transposed by xty. So it's equal to 1.4. Now to find sigma squared, which is what we've been looking for, we divide it by t minus k minus 1. Here, k is refers to the number of the independent variables we have, which is 2. So t is equal to 23 minus k equal to 2 minus 1. So it's 23 minus 2 minus 1. It's equal to 0.007. So r squared is equal to 1 minus the residual sum of squares over the total sum of squares. It's equal to 1 minus the residual sum of squares, which we found here, divided by the total sum of squares, which is given to us in the beginning of the problem. So it's equal to 10. So it's 0.86, which is considered a good fit. So Next question is to test the global significance of the model at 5% risk. What this means is that we are testing the hypothesis that beta 1 and beta 2 are both equal to 0. Each alternative here is that at least one of them is different from 0. So the model hence has some explanatory power. So we go back to Excel to calculate the F value using this formula. So let's start by this part, r squared over 1 minus r squared. So it's equal to 0.86 over 1 minus 0.86. The second part is t minus k minus 1 over k. So t is equal to 23, k is 2, we have two independent variables. We subtract 1 because to account for beta 0, and we divide by k, which is 2. So f is equal to this first part by this second part, which is equal to 61.42. So it's the result we already had, it is confirmed. So we'll be comparing this value to the f from the table. We will be looking at the f table for alpha equal to 0.001. So df1 is equal to k, which is 2, and df2 is equal to t minus k minus 1, which is 20. So 2 and 20, we find 3.49, which is much, much smaller than the f value we calculated. And hence, we are going to reject H0. And hence, we conclude that our model does in fact have some explanatory power. So the next question is, are the returns to scale constant at 5% risk? So what does it mean, the returns to scale? So I have an article here about it. I will share this with you. But to put it simply, testing for constant return to scale means testing the hypothesis that the sum of the coefficients is equal to 1. The sum of the two coefficients, beta 1 and beta 2, is equal to 1. So here are our H0 and H1, and we will be using the t-test. This is actually a test of linear restrictions, but we don't have the possibility to get the restricted residual sum of squares. So we are doing what is called a postpartum test of linear restrictions, which is the t-test. We use the exact same formula we're used to, so it's the estimates minus the value in the H0 divided by the standard error of the estimates. So we get the standard error by having the square root of the variance. And as we learned in our very first session, the variance of beta 1 hat plus beta 2 hat is equal to the variance of beta 1 plus the variance of beta 2 plus 2 covariance beta 1 hat, beta 2 hat. So where are we going to get these variances and the covariance? So we're going to have to calculate the matrix of variance covariance, which is calculated using this formula. It's sigma squared by xtx minus 1. We'll go back to Excel so I can show you the calculations in detail. So we start by calculating the variance covariance matrix, which has this general format. We have the variances in the diagonal, and we have the covariances here. So the values we're going to need are the variance of beta 1 hat, the variance of beta 2 hat, and the covariance between beta 1 hat and beta 2 hat. So to find this variance covariance matrix, we just multiply sigma squared by x transpose x minus 1. We just multiply each element by sigma squared. We find these results. So we're going to be using these values to calculate our t value. So let's start calculating the t value. So here, the denominator, we have beta 1 hat plus beta 2 hat minus 1. Beta 1 hat is equal to 0.7. Beta 2 hat is equal to 0.2. Minus 1, it's minus 0.1. Now, for the denominator, it's equal to the square root of this value plus this value plus 2 times this value, which is the covariance. We do the division and we find our t calculated. It's minus 1.195 and so on. So I forgot to mention this earlier, but here we have a two-tailed test since our H0 has an equality sign. So this is going to be a two-tailed test. So we have to compare the absolute value of t calculated that we just found to the t from the table. So let's go to the t table. It's here. So we have our t table here. We have a two-tailed test, and our alpha is equal to 0.05. So it's here. And our degrees of freedom is 20. So it's 2.086. So let's compare that to our t calculated, 2.086. So the absolute value of our t is smaller than the t from the table. Hence, our conclusion is that we do not reject H0. We will not reject H0. So for the last question, we suppose that beta 1 is equal to 1 and beta 2 is equal to 0. And we give the RSSR, which is the restricted RSS, equal to 2. So this is also a test of linear restrictions, except that we have the value of the restricted RSS. So we will perform an F test. So we'll have H0 is beta 1 equal to 1 and beta 2 equal to 0 against H1, which is the opposite of H0, of course. So this H0 is actually equivalent to this restricted model. As you can see, it doesn't have the variable Z anymore, as we are supposing that beta 2 is equal to 0 and the coefficient of X is 1. We're testing that against our unrestricted model, our original model. So to calculate the F value, we use this formula. We already have the unrestricted RSS, which is 1.4. We calculated it earlier. We are given the restricted one, which is 2. The number of restrictions here is 2. So we do the calculations and we get this value, which is 4.28. We will compare that to the value of F from the table, which is equivalent to Fm t minus k minus 1. Let's look at the table. So it's equivalent to F220, which is the same value we used earlier. So by comparing the two values, we can see that the calculated value is larger than the critical value from the table. Hence, we will be rejecting H0. We'll be rejecting the restricted model. This is it for this problem. Thank you for your attention and let me know if you have questions.